The last part of this chapter, we're going back to talking about solutions, but this time we're going to be looking at the concentration of the solution. There's lots of different ways to measure concentration of a solution, but the one we're going to be using in this chapter is called molarity, and it just gives us an idea of how much solute is present in the solution. Because remember, a solution contains a solute dissolved into a solvent. So the molarity tells us how much solute is dissolved into the solution or into the solvent, okay? So the calculation for molarity is right there, moles of solute divided by liters of solution. So be careful, make sure when you're calculating molarity, you're using liters and not milliliters, because most of the time when we measure in the lab, it's in milliliters. So just be sure to change to the liters. Okay, so do an easy calculation here. So I usually like to write kind of like what we did with density. So molarity is equal to moles per liter, because that way we can rearrange it and say, okay, well, if I have molarity and liters, then I can find moles, right? Or if I have moles and concentration, molarity, then I can find liters. So we're going to be rearranging this equation as we use it throughout this chapter. So again, just be sure, in this question I gave you an easy one, but it's not always how it's going to be. Okay, so we have moles of our barium chloride, 0.56. Oops. Moles. Okay, and they give it to us in milliliters. It's 100 milliliters, but to take it out of milliliters, all we have to do is divide by 1,000. So it's going to be 0.100 liters. And that gives me 5.6 molarity. So big M represents molarity. Okay, let's do one that's a little bit different. This one says, how many grams of sodium sulfate are required to make 0.35 liters of a 0.5 molar sodium sulfate? So I put on here already, molarity times the volume gives us moles, okay? So if I have moles of my solute, but they're asking for grams, I can easily get to that by using molar mass, okay? So molar mass, and then that will get us to grams. Okay, so we'll start with multiplying our concentration, which is 0.5 molarity times 0.35. So we have to make sure our volume is in liters, because if it was in milliliters, it would not cancel out here. Okay. And that gets us 0.175 moles. So that's how many moles we have of our sodium sulfate, and I just need one more step to get me to grams. So I need to multiply by the molar mass. So the molar mass of sodium sulfate is 142.1 per 1 mole. So something we learned in chapter 3. So moles cancel, and I get 24.9 grams of sodium sulfate. Okay, we can also figure out concentration of ions in a solution. So we learned all about how soluble ionic compounds and strong acids and strong bases completely dissociate in water. So since they're dissociate in water, we can figure out the concentration of the ions in the water. So all we have to do is make a molemole ratio between the compound and the ion. So for example, right here, we have 1 calcium, 2 chlorine. So if I have 1 mole of calcium chloride, then I have 1 mole of calcium. Okay, so I just use the subscript in my compound. Okay, if I have 1 mole of calcium chloride, then I have 2 moles of chlorine. Okay, so I use my subscripts to make that multimole ratio. Okay, so then I take the concentration of the compound here, which is 0.3 molar, and I put my multimole ratio in to where my compound will cancel, and I'll be left with the ion I'm looking for. So here I just multiply it by 2 because that's what the subscript was on chlorine, and the concentration of chlorine ions is 0.6 molar. Okay, so pretty much all you have to do is multiply the concentration of the solution by the subscript in the compound. Okay, so when we are making a solution with a known concentration, what we do is we take the mass. So let me just go back here. So here we found that we needed 24.9 grams of sodium sulfate to make a 0.5 molar concentration and 350 mils of it. So if I were to make that, then I would weigh out my 24.9 grams of sodium sulfate that we calculated. Okay, and so 350 mils. So I would get what's called a 350 mil graduated cylinder, not graduated cylinder, I'm sorry, volumetric pipette. And so the volumetric pipette looks like that in the picture. So this right here is our volumetric pipette. Okay, so you can see this little line right here. So if I fill the water up to that line, it's exactly 350 mils, but actually the one in the picture is 250, but we're just going to pretend it's 350 because that's what the last problem said. So we would take our 24.9 grams of sodium sulfate, we would pour it into that flask, and then we would put water up to the line, the 350 mil line, and we would dissolve it. So that would give me exactly the 0.5 molar concentration that I was looking for. So that's how we make solutions with known concentrations. So it's important to do it that way, because if you were to just take 350 mils of water and then pour your 24.9 grams of sodium sulfate into it, that's adding volume to your solution. So it's no longer just 350 mils. Now, since you poured the solid in, now you will have a higher volume. So that's why we make solutions with specific concentrations using these volumetric flasks, because we want the solution to be exactly, the 350 mils or however many mils we're looking for. Okay, anytime I add water to the solution, it's called diluting the solution. Okay, if I add water to my 350 mils we just talked about, it's going to be more dilute, just means it has more water. Okay, so the ratio of the water to the solute, the amount of solute in the solution increases, and so my concentration goes down. Okay, if we wanted to make a new solution from the solution we just made, okay, we had 0.5 concentration in our 350 mils of sodium sulfate. If I were to make a diluted solution, I would take the volume out of the solution I just made, put it into a new beaker, add water, and now I have a new concentration. Okay, it's going to be lower because you just diluted it, but I can do that. And if I want to figure out the concentration of my new solution, then I just have to use, I don't know why this is like that, but it's M1 times V1 equals M2 times V2. So this equation is only used for dilutions. Okay, you can't use this for the next thing we're going to talk about, which is the titration. You can only use it for dilution. Okay, I'm going to put an example, whoops, right here. Okay, so I'm going to continue to talk about that solution we pretended to make. Okay, so we added, what was it, 24.9 grams of our sodium sulfate. Whew. Pen went crazy. Okay, we added 24.9 grams of sodium sulfate, and that's giving us a concentration, actually, oh, for goodness sake. Okay, our concentration, our molarity was 0.5. Okay, so anytime we make a solution like that, we call it our stock solution, because we can take the stock solution and take some volume out of it and make diluted solutions. Okay, so we can make a solution out of this one. So we're just going to take out of the stock solution, put it in here, and then we'll fill the line up to, let's say, 250. Okay. And let's say we took out 15 mils of our stock solution to put into this new beaker. So 15 mils of our stock solution, we filled the water up to the 250 line. So the question is, this new diluted solution, what is the concentration? Okay, so M1, let me go back here. M1 is the concentration of the stock solution. Okay, so this right here is our M1. Okay, that's the concentration of the stock solution. M2 is what we're trying to find. What is the concentration of our diluted solution? Okay. Now V1 says it's the volume of the stock solution that is used to make the diluted solution. So this is V1 up here. So I took 15 mils out of my stock solution to make my new solution. So that would be my V1. Okay, and then, where am I going? V2, it says, is the total volume of the diluted solution. Okay, so this right here would be my V2. It's the total volume of the diluted solution. So to be able to calculate M2, we're going to use M1 V1 equals M2 V2. Okay, so we know M1 is 0.5. We know V1 is 15 mils. Okay, we're solving for M2, and we see V2 is 250 mils. Okay, so on this, even though molarity has to be in liters, because both of the volumes are in mils, you don't have to change it to liters. Okay, they're just going to cancel out, so don't change it to liters. Okay, so we're going to take 0.5 times 15, and then we're going to divide the 250 and solve for x, and we find that our M2 diluted down to 0.03 molarity. So we started with a 0.5 concentration. We only took 15 mils out, we added a lot of water, and now our concentration is 0.03 molar. Okay, so we're going to do another problem like that without drawing beakers. But I just wanted to be real specific on what M1, V1, M2, V2 is. That way when you have a problem, you can figure that out, okay? So it says how many milliliters, so we're solving for volume, of 3 molar sulfuric acid are needed to make 450 mils of a 0.1 molar sulfuric acid, okay? So let's just label these real quick. So we're making a diluted solution that contains 450 mils. That's our V2, right? Total total amount of the diluted solution. This is going to be M2 right here because it's the concentration of our diluted solution. And then up here is M1 because that's the concentration of our stock solution, and we are solving for V1. So we want to know how much are we going to take out of the stock solution to make this new diluted solution. So we're going to take 3 times V1, that's what we're looking for, is equal to 0.1 times 450 mils. Whoa. Oh, for goodness sake. Okay, so we're going to take 0.1 times 450 and then divide by 3, and that gives us 15 mils. Okay, so we had to take 15 mils out of our stock solution, and we added water to 450 mils, and now we have a concentration of 0.1 molar. Okay, the last part is titration. So titration we use in able to find the concentration of an unknown solution, okay? Or, I mean, we know what the solution is, we just don't know the concentration. So a titration is a great way to find that concentration. So I'm going to jump to this picture. Okay, the setup looks like this. Okay, and we're going to be doing an acid-base titration. So your acid is going to be in the flask. So down here is your acid, and your base, this pen, is going to be in the burette. Okay, so we either don't know the concentration of the base, or we don't know the concentration of the acid, and that's what we're searching for. Okay, we know what the makeup of the acid and the base are, we just don't know what the concentration is. So to do a titration, let me come back here. We have to use an indicator, what's called phenolphthalein. So in an acid, phenolphthalein is clear, but in a base, phenolphthalein is pink. So you have to use the indicator in this. If you don't, you'll never know when you reach the equivalence point. Okay, so the equivalence point is when you have stoichiometrically the same amount of acid as you do base. So basically, the goal here is to get this faint pink color, because if I have a clear solution, that means I have more acid than I have base. If I have a hot pink solution, then that means I have more base than I have acid. So if I want to get stoichiometrically the same amount of acid and base, then I need to have this faint, very faint pink color in my solution, so I don't have more acid or more base. It's not super easy to do, but it is possible. Okay. So once we hit that faint pink color, we know we've reached our equivalence point, but we also call this the end point. Okay, when the faint pink color shows up, that's called the end point, and that lets us know we've reached the equivalence point. So I'll just write this on here. So end point is the faint pink color. Okay, so we know we want to stop titrating when it's faint pink. So in the picture, that pink is actually too pink. So you want it so faint, you have to hold the paper towel, white paper towel, up to it to actually see the pink. Okay, so for titrations, the calculations are always using stoichiometry. So if you had trouble with stoichiometry in chapter 3, you may want to go back and review that, because that's all titration problems are, is stoichiometry. Okay, so the first thing we need for a titration problem is a balanced equation, right? Because with stoichiometry, we use balanced equations. So we are going to make our own chemical equation here because this is an acid-base reaction, so we know how to do that. So it says we have sulfuric acid, okay, and we have sodium hydroxide. Those are our reactants, and it's going to produce water and sodium sulfate. Not sure I'm going to have enough room, so I'm going to put it down here. Okay, so we know with the balance, or I'm sorry, with equation, you have to balance it. So here we have 2 sodium, we need 2 sodium here. Okay, and then we have 4 hydrogen on the reactant side, we need 4 hydrogen on the product side, 1 sulfate, and then 2 oxygen, 2 oxygen. Okay, so that is our balanced equation. You must have that in order to do the titration problem. Oops. I'm going to jump over here now. Okay, so the question's asking, we have 11.6 mils of a 3 molar sulfuric acid, and they are required to neutralize the sodium hydroxide, and we had 25 mils of sodium hydroxide. What is the molarity of the NaOH solution? So we're looking for the molarity of the base. Okay. So we already said we have H2SO4 plus 2 NaOH going to 2 waters and sodium sulfate. Okay, we have to have that balanced equation. Okay, so the reason we have to have the balanced equation is we're always going to use a multimole ratio in a titration problem. Okay, so they give us the concentration of sulfuric acid, and usually when I write this, I don't like the molarity. I always write moles per liter. I don't write big M usually, because I like to see things cancel. So we're using stoichiometry and conversions in titration problems. Okay, so if I multiply the concentration of acid times the volume of my acid, so I've got to divide by 100, I'm sorry, not divide by 1,000 to get my milliliters in liters. So instead of 11.6 liter, oh my gosh, 11.6 milliliters, I have 0.0116 liters, so that cancels out. Okay, now I have moles. Now I can get to my multimole ratio. So the question here is, what is the concentration of sodium hydroxide? Well, I need 2 things to find molarity. I need moles of sodium hydroxide and volume of sodium hydroxide. Well, the problem told me I have 25 mils of sodium hydroxide, so the only thing I'm missing is the moles. And I can do that, and I can find that from the multimole ratio. Okay, so we know there's a 1:2 ratio. So 1 mole of H2SO4 to 2 moles NaOH. Okay, so that cancels, that cancels. Okay, now if I multiply this out, I find that I have 0.0696 moles of sodium hydroxide. So that was my missing piece to calculate the concentration of sodium hydroxide, because now all I got to do is take those moles and divide it by the liters. So they gave us 25 mils of sodium hydroxide, but divide that by 1,000 and I have 0.025 liters. So that's going to give me a concentration of 2.78 molarity. So again, you will always use that multimole ratio when you're doing titration problems. So not all titration problems look just like this. Sometimes we can solve for the volume of the acid or the base. Sometimes we can solve for the grams of the acid, okay? So you have to be careful because not all titrations look the same, but they all will use a multimole ratio. Okay, let's do the next one. So it says, how many grams of calcium hydroxide are needed to neutralize 25 mils of a 0.1 molar concentration HNO3? Okay, so let's do our balanced equation. I'm going to do it over here. So we have calcium hydroxide, and we have nitric acid. Okay, so we know that's going to produce water and calcium nitrate. Okay, so we have to balance. So we have 2 nitrates on the product side. So let me switch colors here. Okay, 2 nitrates on the reactant side now. We have 4 hydrogen on the reactant side, so I need 4 hydrogen on the product side, and that is it. Okay, so it says we have 25 mils of our 1 or 0.1 molar base. Okay, 25 mils. And we want to know how many grams do we need to begin with of calcium? Oh, wait. Yeah, I'm sorry, calcium hydroxide. Thought I was looking at that wrong. Okay, so again, the goal is to get to the multimole ratio. And if I find moles of calcium hydroxide, then all I have to do to get to grams is just go grams to moles using molar mass, okay? So let's use what we have, which is our concentration and volume of base. So moles per liter, it's the concentration of our, not our base, I'm sorry, of our acid. And then if I multiply by volume, again, I have to divide by 1,000. Okay. So liters cancel. Okay, but I want to go to the multimole ratio. So now I have moles of my acid. Now I can get moles of my base. So it's going to be a 1 to 2. So 1 mole of my acid to 2 moles of my base. Nope. I did not write that right. I'm sorry. Oh, okay, let's try that again. 2 moles of my acid. 1 mole of my base. Okay, so that gets me moles of calcium hydroxide. And then I can go moles to grams using molar mass of calcium hydroxide. Okay, so our moles are, let me see here, I don't actually have those. So point. Okay, our moles of our base are 0.00125. Okay, and then using the molar mass of calcium hydroxide, which is 74.1 grams per 1 mole, I get 0.0926 grams of calcium hydroxide. Okay, are needed to neutralize my nitric acid.